Hi everyone, in this work we investigate the reasons behind the high variance in gradients and differentiable BA layers and propose a simple solution to mitigate this variance. Differentiable BA layers are commonly used in conjunction with deep networks to tackle various pose estimation problems such as SLAM, visual odometry, SFM, and various object pose estimation tasks. In this work, we use one of the state-of-the-art approaches to solving the visual odometry problem, namely DPVO, as an example to analyze differentiable BA layers. The main components of this work are the update operator and the bundle adjustment layer. The update operator is a neural net which estimates the correspondences between the frames, delta, and the associated confidences, sigma, given some poses and depth estimates, T and D. The bundle adjustment layer uses these correspondences and confidences to solve a weighted least squares problem to update the poses and depths. These two operations are repeated several times to obtain the final pose and depth estimates, which are then used to compute the flow and pose losses against the ground truth values of the poses and flows. The losses are optimized using a standard stochastic optimizer to obtain the network parameter updates. However, we observe that this model is very slow and unstable to train and undergoes large fluctuations in the validation ATE errors across training. We further observe that throughout training, the model gradients also suffer from very low signal-to-noise ratio. We hypothesize that all these three issues are a direct result of high variance in the model gradients stemming from having to differentiate through the BA layer. In this paper, we explore the factors affecting this gradient variance and propose a simple solution to mitigate these issues. We find three components contributing to this variance. The first component, namely the weight residual dependence, arises very simply due to the multiplicative interaction between the correspondence residuals delta and the confidence weight sigma. Specifically, a high variance in the residuals, for example, due to the presence of outliers, directly corresponds to a high variance in the gradients on the confidence weights. The second component arises from the linearization errors within the BA problem, that is, high variance in the pose or depth estimates leads to high variance in the linearization Jacobians, which correspondingly leads to high errors in the gradients backpropagated through the BA layer. Lastly, and perhaps the most important, we observe that the multiplicative interaction between the poses and depth variables when computing the flow loss results in an increase in the variance in the corresponding gradients when the variance in either of those two variables is high. Interestingly, we observe that all these three errors get exacerbated by the presence of outliers in the inner or the outer problem. We design toy experiments to artificially introduce variance at various points in the BA problem and see a corresponding increase in the gradient variance. This clearly shows that even empirically, a rise in the noise or the number of outliers results in a corresponding rise in the gradient variance. In this work, we present a very simple solution to address this issue. We simply weigh the flow loss computed at the output of the layer with the corresponding confidences, sigma, spit out by the network. This allows the network to deprioritize noisy points, thereby significantly reducing the variance of the flow loss gradients. However, given the distribution of confidences could vary throughout training, it also helps to dynamically weigh the flow loss against the pose losses to balance the gradient contribution of the two terms. With this simple modification, we observe that the variance of the gradients reduce significantly, thereby boosting the signal-to-noise ratio. The effect can also be seen in the validation ATE plots, as it results in faster and stable training and converges to much lower validation ATEs. We observe that the modified objective transfers well to other settings as well, with little to no hyperparameter tuning. For example, the third plot here shows the improvements offered on Droid SLAM, a slightly different method which also uses differentiable BA layers to tackle the visual odometry or SLAM problem. The improvements in validation performance also transfer to the tartnet test set, where we obtain significant improvements in the ATE across environments. However, we observe that the improvements don't necessarily translate to out-of-distribution datasets. This is not surprising, as the transfer performance across datasets is dominated by other orthogonal components, such as the network representation and dataset quality. Finally, we would like to note that our method is but one of many possible strategies one could try to reduce the gradient variance. However, to our surprise, despite significant effort, we find that most such strategies offer rather marginal to no gain, as they typically also introduce bias which results in higher final losses. This underscores the significance of the improvements we obtain given the simplicity of our suggestions. Our work is an initial attempt at understanding the numerical issues stemming from the usage of BA layers and optimization layers more broadly within DL pipelines. We thank you for your attention and hope to see you at our poster.